Welcome back. In this follow-up video to the last example, we're going to look at how to visualize tangent lines to level curves in Mathematica. MMA is short for Mixed Martial Arts. No, I'm just kidding. MMA is short for Mathematica. So we're going to look at how to visualize tangent lines using Mathematica. The example we were working on in the last one was to find a tangent line to the level curve of the function f of xy equals x squared plus y squared associated with the constant 4. We remember that the level curve that we generated was given by the set of all inputs x comma y such that x squared plus y squared was equal to 4. Always, when we're looking at a two-variable function with a single output, the level curves are subsets of the domain space. So this is a curve in R2 that represents input. When we try to find a tangent line, we chose a point on the curve, which was given by square root of 2, comma, square root of 2. This was the point along a 45-degree angle. We saw that in general, if we wanted to get the tangent line to this curve, we needed the slope of the tangent line, which of course is the derivative, and we use the technique of implicit differentiation from Math 1a to find at any point x comma y, the slope of the tangent line is negative x divided by y. We can combine this with Math 1c to recognize that such a line would be in the direction rise divided by run. Well, the x coordinate of the direction vector would be the run, so it must be the y coordinate of the point. And then the rise would be the amount that you go up or down, and that must be in the y component of the direction vector. This led to a parametric equation for that line given by r of t here. We're going to switch over to Mathematica and actually graph the level curves, the contour curves, and then this tangent line to the level curves on the same graph as the level curve to see that we're not just going crazy. Well, we are going crazy, but we're crazy in love. Yeah, I'm going crazy in love. I wanted to say something kind of cool though. Way back when in Math 1a, do you remember seeing implicit differentiation and being like, okay, well, I can do this, but what the hell would I ever use this for? In truth, we didn't tell you back then that the tangent lines, slope of the tangent line that you were calculating using implicit differentiation was actually coming from intersecting a plane with a three-dimensional surface and then drawing tangent lines along that plane. Later in this course, we'll talk about why this is important. Anybody that's ever done a kick turn on a slope understands the idea of a tangent line to a level curve. If you've ever gone down a really steep hill by doing switchbacks, those are tangent lines to level curves, or at least slightly askew to tangent lines to level curves. My claim is you understand this in your bones when you're standing on the top of a steep hill. This is the formal mathematical technology used to take intuition and bring it into a place where you could model and make money in that modeling. Shut up, Jeff, and switch over to Mathematica. Okay, here we go. Here we are back in our Mathematica playground for lesson 7. We're going to go ahead and graph the function that we were looking at, which was going to be a two-variable function, and it was defined as an elliptical paraboloid given by the pure x squared plus y squared. We saw that the level curves of this sucker were circles, which makes sense from the standpoint of how this is written. Let's go ahead and plot 3D. We'll open and close brackets immediately. I don't know if we want to end our plot 3D command by labeling where the end is. This is a great technique. Takes 2 seconds, but it can deal with a lot of headaches as you get better at coding. So let's go ahead and graph f of x comma y. And I remember that the level curve we were going to look at was at 4. So perhaps the input values should range from, like, I don't know, negative 5 to 5. That would get me up to about, that's going to get me to 50, isn't it? If I go both negative 5 to 5 and x and y. Maybe that's too big. Let's go negative 3 to 3. If I think that will get me up to about what? 18. That's a little bit better. And then we'll look at plot range. And we'll go, what did I just say, 0 to 18? So that should get me that particular level curve. Did I miss something? 9. I want to do 20. No, that's not really big enough. Let's go out to 5 here. So I guess I was doing something crazy. So let's go out to 5. Yeah, that's a little bit better. Okay, you see the clipping style? It's kind of giving me a headache. Let's go down to 10. Yeah, there it is. Okay. So let's turn the clipping style off. We'll say clipping style, leave me alone. So false it. And then, I don't know, my anti-proclivity against meshes is kicking in. So I say mesh off. And then, of course, I'm going to want a plot style. I hope you've been noticing that the order which you do these attributes, the different things that we're looking at, doesn't really matter. As long as the first one is the function and then the next two are the input constraints. The rest of these you can do in any order. I'll show you that in a bit. I like blue, of course, and opacity, perhaps 0.5. Let's be a little bit more happy. Let's a real mathematicians graph in pink. Okay, so there's my pink. And what I wanted to show you was if I switch the order of these, there's not gonna be an issue, as long as I take care of the commas correctly. That's pretty amazing. That's a very special thing about Mathematica. My hat's off to Wolfram. So what we're gonna do now is we're gonna look at the contour plot that comes from intersecting our curve with the appropriate plane. And remember, the plane that we wanted to look at was z equal to 4. So here we'll use contour plot 3D, and we'll go ahead and look at the plane z equal 4. If we're going to do this, we might as well keep the same input and output values. Of course, this is not a plot range because this is the range on z. So now I can go ahead and graph that thing. Of course, it's not in the colors that old Anderson likes. So what's really cool is I can now just take my plot style and change it to contour style. This is not a plot, it's a contour. So the style better be of contour. And then of course, I don't know, should I be lazy? Always. We'll take mesh and turn that sucker off. Okay. And let's do blue here just to make it, okay, or maybe green. Maybe you're sick of blue. Maybe you're like, Anderson, you need to get a life. Yeah, it's true. Okay, so now let's go ahead and graph the contour curve. The contour curve is the curve in R3. So remember, this contour curve is going to be given by a circle. What is this going to be? Parametric plot 3D. And we said that circle was going to have radius 2. So remember, when I do circles in parametric plot, this is the vector valued function stuff that you worked in lesson, what was it, lesson 5, I suppose? Very powerful lesson, wasn't it? Okay, so we said that that particular plot would look something like this, and then we would go from 0 to 2 pi if we wanted the exact or the entire circle. And then of course this is going to be a plot style, and maybe just copy and paste. I don't know, it doesn't really matter, you could type it out. So I think we're going to do green here, and this is not going to be opacity, this is going to be thickness, and I always forget, maybe 0.1. I can already tell mathematics, because did you see that little pink thing right here? I don't know if you can see this in your screen. That tells me that this is an error and I should delete it. So if you ever see a pink highlighted comma, it means if you actually use that, cause issues. Okay, so there's my contour curve, which is the curve in R3. I don't really like that, actually. I want to go back to blue. I think blue will give a better, yeah, that's a little bit better, right? So it's the intersection of the plane z equal 4 with surface. Of course, the curve itself happens without the plane. So really, that's the contour curve. It's the curve along the surface. And remember, what we're going to do now is that curve is graphed in R3. You can see it on the edge of the surface. And if I walked along that curve, I would not change my elevation. I wouldn't change my z value one bit, because it's all all values along the surface that have constant z equal 4 values. Remember that the level curve comes from graphing that particular curve, but projecting it down onto the xy plane and pretending like the xy plane is in R2. So to do this, we're going to use contour plot, and then we're going to plot the x squared plus y squared equal to 4. And of course, we should probably use the same x and y range. It's complaining about something, and maybe I use a contour style that's pretty similar. So something like this. And this, of course, probably would be thickness, would be better than opacity because it's not a surface. It is a curve. Okay, so there's my curve. That's a little too thick, huh? So it's still a little too thick. Let's go down to like that. Okay, there we go. So there's my level curve, and that level curve corresponds to the contour curve. Maybe if we really wanted to, maybe we call this lowercase level, and then we suppress this output, and maybe we call this thing contour, and we suppress this output. And then we can use graphics row, which just literally produces two graphics in a row. It's very similar to show in that way. And we write contour as the first one and level as the second one. What are you complaining about? Oh, I haven't actually set this into memory, and you can see that because it's blue, right? Okay, so now we go. Oh yeah. Mathematica expects this as a list, so I need to add the brackets. There we go. There we go, there we go. See it? So here on the left-hand side, I see my contour curve. On the right-hand side, I see the level curve corresponding to that. Let's go back up to this level curve and just go ahead and steal this code. So I like to think about this. Right now, we're not producing code for anybody but ourselves. If I was paid to produce code to solve a problem, I would not be as cavalier with the way that I write my notebooks. One of my really dear friends from graduate school used to call this a sandbox. When you play in a sandbox, you can do whatever you want. This notebook is not, I'm not getting paid for this, and I'm just literally playing. I'm playing in my sandbox. Okay, so here we have our contour curve. Remember that we also found an equation for the tangent line to this curve at a particular point. So the first thing we're going to do is let's go ahead and graph that point. And the way that we're going to do that is use a graphics command. Here we're going to go ahead and graph the point. We'll start by identifying the point size, which we'll call 0.02, I think was a good one. We'll use the point command. The point command expects a list, so I use brackets. And the first one that we had, I think, was a square root of 2. Ooh, what did I just do? Oh yeah, that's right. Square root of 2, and then the second one was square root of 2. And then we'll go ahead and graph that. Let's increase the point size to make it a little bit easier to see. What we see immediately is that that point is indeed on that curve. The next thing we were going to do was to actually draw a line, and the way that we're going to do that is to graph the parametric curve that we determined in the earlier video, and then we reviewed at the beginning of this video. That parametric curve was given by something like square root of 2 plus t. And then, of course, we said square root of 2 minus t was the y-coordinate of this thing. And perhaps we say that t goes from like -1 to 1. And, of course, if I'm going to do this correctly, maybe we determine a particular color. So since this is a plot command, I'm going to go plot style, and we'll give it a directive. I like maybe red for this one, and we'll go thickness. Perhaps we'll use 0.01. Let's see how that is. It doesn't look like it gives me the full tangent line. Maybe I want to go out from -4 to 4. And of course, if I went to 0, it would only give me half the tangent line, right? So that's kind of fun. Changing the domain changes this. This is a little bit thicker than I would want it. Okay, so there we go. There's the tangent line. Something that's fun here is if you switch the order of these graphics, Mathematica kind of has like a layering effect in the same way that you expect Microsoft Office or Microsoft Word. Did you see that now that the point is last, the point is overlaid the line, whereas if I did the line last, the line overlays the point. So what you see there is that you have a level curve which corresponds to all of the points in the domain that give me a standard a constant output value. And then the tangent line to the level curve touches only at the point and goes in the direction of the tangent vector. I also wanted to notice that we could very quickly change this. Let's pretend that you wanted to do the point over here, which has a negative. Remember that if this has a negative, one of these is going to be negative. So let's see, if this was a negative, that would mean that the point had a negative here. And then we looked at negative x divided by y, which was the slope. That would be negative square root of 2 divided by square root of 2, which would be positive. So both of these would end up positive. So I just did that in my mind. You can confirm that. I could also do the, I mean, you could start doing anything you'd like, but what you notice is that you can move this tangent line around this curve. That gets us a pretty good introduction to visualizing tangent lines to level curves. We're going to see this again in lesson 11. I'm actually setting you up like Draymond Green to Steph Curry for an alley-oop once we get to lesson 11. And I hope at that point you'll have a huge smile. Nice work, y'all. I'll see you in the next video.